Hi, welcome to lesson 4 in the series of 8051 microcontroller programming and interfacing. You can also visit us at www.jcbrolabs.org and you can download the slides and the web page content of the same lecture from that website. In our last lecture, we discussed about the various instructions mode of 8051 microcontroller and the several instructions which are available in assembly language for programming a 8051 microcontroller. So today we will move forward and today we will talk about the simulators. We will talk about especially the compilers or the assemblers for writing or for assembling the 805 microcontroller assembly language program, and we will write several programs in assembly and we'll try to run and we will simulate all those programs as well. So when we talk about assembler, okay, we have learned up to like we will write a assembly language program code, but ultimately we need a hex file which required to burn inside the microcontroller or which required to be programmed inside the microcontroller. So we require some IDE, integrated development environments, or some softwares, or in other sense we require some assemblers which can do this work for us. That means we will write instructions in assembly language, and then these particular assemblers or softwares will convert that assembly language program into hexadecimal file. And one of the benefit for those programs as well, we can also debug our program before burning the same code into the microcontroller, so that it helps or it saves a lot of time. Now there are several assemblers or softwares which are available on internet, but Keil Keil is one of the famous assembler or IDE environment for assembling or compiling these 8051 microcontroller programs. So we will be also using the same Keil IDE in our tutorial series. So in this particular video we will go step by step how to use Keil and how to make program on Keil, and then we'll move forward. So let's open Keil. So its latest version is also available to download. So it is evaluated version so that it can only compile a code of 2 kilobyte size only. And in Keil these are the various options which are available. So we first go here, we create a project. So go to new microvision project, and then we can select a space from where we want to create our project. So we are making it on desktop, so we suggest create a folder name like lesson 4. Create a folder so that all the files which are being generated additionally with the Keil, they can be put at the same place. So we will we will name the project file. So let's say it's lesson 4, and then save it. As soon as we save it, asks for the microcontroller, or like on which for which microcontroller we are writing the code. So there are several microcontroller companies and Keil has listed. So we'll be writing one of the commonly used microcontroller for general purpose and for study is 89C51 or 89S51. So in our upcoming videos we will be using 89S52 and 51 series microcontroller. So let's choose the same because these are easy to program. This S52 series of microcontrollers are easy to program, and we will discuss more about it later. And let's choose it. Okay, and yes. Now the next thing is our project is done, project is created. Now we need to create a file. So go in file menu and choose new option. This text window will open up. So first save this text window as save as, and remember when we are writing the code in assembly language, so then we need to save the program in .asm format, which indicates the file is of assembly language. then save it. Now we need to add this particular file into our current working folder, and let's also change the font size so that it is more visible to you. Let's say we are the font can be changed from a select 8051 editor ASM files, and then we can change the okay, its size is direct by default 18. Okay, and okay, it is already 18, font is there. We can also set several other things from here as well, like font memory window. So we can have the font size of 16. Okay, and then we have logic analyzer. Okay, edit your text file. We can also have its font size 16, and all the things we can do. Okay. Okay, so now next step is to this was for the convenience purpose only. So next step is to add this particular file into our current project. That can be done from here. Go to project, then go to manage, and then components and environments. Now click on add files. Now here no files being shown because by default it is C source file, so we need to select the ASM source file and our file will be there. Just click once, add, and our add file will be added here, and then okay. As soon as we add file, our file will be displayed to this section. So it says like now our file has been added to the project. Now there are some other options as well. Options like let's say options for target one. So generally these are the options or environment settings which we want to set. So like megahertz frequency. So generally we will be using 12 megahertz frequency for the microcontroller, and then output we want to create a hex files as well for our output. So this can be set from here, and then okay. Now we are ready to write our first program of 8051 microcontroller. So we can write assembly codes in capital and small letter. There will be no change in the instructions. So for our convenience we will be writing in capital letters only. So it starts with org00h. It states this particular instruction, or this is the directive org origin directive. It says like whatever program we are writing, that will start in from 00 location in the ROM memory location. So if we write like 30h, so our program will be starting from 30 memory locations. Now let's go to next instruction. So we will be simply doing normal operation. We have discussed the internal architecture, so there were several registers and accumulators. So we'll do simple one. We'll move some data into the accumulator. So as we discussed last, if we hash sign, right, like hash sign, then whatever data is there, that access the data. And then last directive is AND. This AND is necessary in assembly language. It tells like okay, the program has ended here. So this is a simple program, and it transfers the 54 data into the into accumulator. So now we will compile it. Compile can be done from here, build target. So build target, and everything goes fine, so all the instructions are fine. It will show 0 and 3 1. Now our program has been done. Now we want to check it. So there is an option, debug option is there. So from this debug option we can start debugging our code. So as soon as we start debugging, there are several things. These are the internal registers of the microcontroller, this R0, R1, and these are their values. Let's see whether we can increase the size of it or not. Assembly debug command window. Okay, this is the debug command window. This size has increased. Now let's say put across the space. Or this particular thing can't be increased. Okay, so if you look at this side, all this R0, R1, R2, R3 will be shown, and here their values will be shown. Now let's this for a search. Okay, now let's compile. There are two options here in debug. There is run option, and then there is step into and step over. So if we press this run options, all the code will execute in simple go. So let's go there and put run. All the instruction has been executed, and as soon as we have put 54 accumulator content, some data has been moved into 54. Okay, let's see. There is a change here. It is 36 while we have put 54 here. So what is the difference? Now the difference is when we write an assembly like 54, so by default it takes its a decimal value, but the values which are being shown here, all these values are in hexadecimal. So let's try to go out of this and let's try to change it and put an H sign there, and then build it again, build target. It is also, you can find it from here, build target, and then debug. So last time we just pressed this complete sign, now we'll press this step over. So this instruction is executed. So now accumulator content is written for, because it is exactly the same which we have written. Now if you check the program status word and all these things, these are by default is 0-1 parity, and all this this particular it shows like number of ones or fours in accumulator. So if we talk about 0-1-0-1, it's 5, and then 0-1-0-0, so there are 3 ones in accumulator content, so it is odd number of ones. So that is why the parity flag has been set. If you remember, we discussed about the PSW last time in last lecture. Okay, so there is a stack pointer is by default C. Now program counter, content of the program counter is 02. Now this particular instruction take 1 byte, and here it is as AND. So now let's move forward and let's add some of the instruction to that as well, and then say R0 right FF. So this thing is here. If we write some data into if data is starting, which is going to be transferred into any register, is that is starting from any alphabetical number, so we have to put a 0 prior to that. So now we'll move R0 into in R0 content, and then we can set move, let's say we have another register R2, and then hash 45H. Now as we discussed, by default these were register bank 0 registers, this R0 and R1. So right now PSW content is 00. Now let's one by one. As soon as you move 54, parity has become 1 and accumulator data is 54. And then okay, I think we didn't compile the program, so it is not executing the next cycle. So we have compiled it now, and let's run it again. Move, and then next instruction in R0 we have transferred FF, and then one more time R2 45 has been set. Now if you look at the program counter status, now it is showing the 06 because it has ended. So let's run it again, reset, all the data has been 0 0. Let's run it again. Okay. Now check the program counter status. It's right now 0 0 when we instruction first command. Now its next instruction to be executed at 0 2 location, because if we say 0 C, this is a code memory. If we write in address like C colon 0x00, so C for code memory. So right now in our code memory, these are the hex codes which are being what are the we can say hex code for this instruction, this move instruction. So this is at 0 4 location. So this is the instruction move A, and this is the data. Then next instruction move R0, the hexadecimal code for move R0, and it is the data. So this is 0 0 address, this is 0 1, this is 0 2, this is 0 3, this is 0 4, and this is 0 5. So when a program started to start, its address was 0 0. When move instruction has been executed, its address is now 0 2, because it is a 2-byte instruction. But that exactly is here. Its address is 0 2. Now if we move forward, now its instruction, because it is executing the next instruction to be executed at 0x04, which is staying here. Now we'll run it. So this is how program counter works. It access the it remains the address of the next instruction to be executed. We can also check the data memory, and I think that can be accessed from like this one. So this was the data memory or the RAM location. So if we are right, mem location goes up to FF, so its highest address is up to FF here. So now if you see the accumulator, this was in the R0. So R0 address, it is register bank 0, that was 00 address, so the content is FF, and R2 was 02 address, that was 45. Now I think its basic is done. Now we want to, let's move forward to do some other programs. Interesting. So now let's say we have paint. Okay, now what we want to do, we want to transfer the data into R0 of register bank 2, and then R1 of register bank 3, and R2 of register bank 0. So what is our objective to write a program? We want some of the data into R0 of register bank 2, R1 of register bank 3, and R2 of register bank 0. So if you remember from our previous class discussion, if we want to set the different register banks, we need to change the content of the PSW. So PSW is bit addressable. We can either change by the same instruction, like suppose we want to set the register bank 1 data. So this was the PSW status 1 2 3 4 5 6 7 and 8, 0 1 2 3 4 5 6 7. So there's one thing, if we transfer, because we want to set register bank 0, so this should be the content of the PSW, and right now because this is RS1, RS0, so its hexadecimal code is 0x10. So if we write an extra command like move PSW comma hash, it was 10h, so we'll select the register bank 0. Now register bank 0 of register bank 2 will be selected, and the data will be transferred into that. Now our second objective was, now we need to change the content of PSW comma hash. Now we want to select register bank 3. So for register bank 3, the content of the PSW should be 11000. So it will be 0x18. It is making 8. So let's say 0x18h, and it is move r1 comma hash. Let's say we are transferring 25h data. Now we want to select the register bank 031, so its content PSW should be 0x00 because everything should be 0. So we'll set PSW comma hash 0x00h, and this register bank 2 data will go into register bank 2. Okay, now let's say it seems fine. Let's compile it. So illegal character and numeric constant. Okay, so it should be 00h. It's already in. So it's compiled 0. Let's debug it and let's run it one by one. This is our data memory. This is obviously our code memory. So these all are the hexadecimal codes of this one, and this data memory. So we'll keep on checking. You can think of it as a RAM locations. So let's move first instruction. A 54 has been set into A. Next, PSW content has been set because they are also parity flag is set. So 10 has been set into it. So now let's say move R0, and R0FF is here because it shows the register data. But look at here, this R0 should be if it is of register bank 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and this is R0. This particular location is R0 of register bank 2. That is why it has been set to FF. Now let's move forward. Now it's content 8, so register bank 3 has been selected. That is why all the content of it has become 0, because right now it is showing the register bank 3 data. So we'll execute it. So register bank 325h has been selected. So this is here, it is register bank 1 of the register bank 3. Now let's move forward. Register bank 0 has been selected, and if we put 45, this 45 has been there. So this is how we can change the particular content, or we can select any particular registers as well. So let's stop it. Okay, now this for the register bank. There was another command which we discussed last time, that was push and pop operations. So we remember. Now we'll write some code. Okay, so what we'll do, we will comment all the all of this. So there is either semicolon or this command, you can comment it out. Now we will learn how the push operation is done. Push command is done. Remember, our stack was starting from 08 memory address, and first of the stack pointer content was 07. So now let's say, let's put some of the data into R0, like hash 05 h move R1. So these are by default register bank 0. And now the thing is, push command, if we want to push the content of this R0 onto the stack, we'll write push 00h 00h. Okay, so this 00h means this is the memory address so of RAM. So whatever data is residing at that particular memory location, that will move to the stack. So push, and then here it comes the address. So suppose we have put some data into R0 and R1 of register bank 0. So we want to push the data of this one onto the stack. So we need to instruction will be like push 00h, and let's see, and then push 01 because R1 data is there. Now when we want to pop it up, so we can pop. Now this is whatever the present content of the stack pointer is, and pop it removes, we write it like 53h, pop 53. So whatever the position pointed by the stack pointer, that particular content will be transferred to this particular memory location, and then stack pointer will be decremented by 1 to other location. So if I'm writing pop, let's say we have some other address 01f h, so this will pop the data from stack to 1fh, and then pop 1 or 20h. So what exactly this program is doing, this is first we are storing some of the data in R0 and R1, then we are transferring the R0 and R1 data onto the stack, and then we are popping back. So let's see how it works. So let's first compile it. Okay, build target, and then let's debug. Okay, so this is our data memory again, and this is our code memory. This is the hex code, and these are the various registers. So let's move one by one. R0 04, R1 65, fine. Now first push operation is there. So remember, right now our stack pointer at the starting of the push is 07. So as soon as you press push command, stack pointer increment to 1, and whatever data is there is stored at that particular location. So right now if we press a push command, this stack pointer will become 08, and at 08 location, because by default the register 0 of register bank 1 will get 04. Let's see, yeah, here 04. So 0 1 1 2 3 4 5 6 7 8 0. So register 0 data has been transferred to the stack. Now stack pointer content is 1. Now move forward, it's 65. So register bank 1 data has been moved to 65. Now we can pop it back, like if we say pop, a stack pointer has been reduced, and 1f at 1f location. So this is 1c, 1d, 1e, and 1f. So whatever post, because it was acting like last in first out, let's say it was last in first out. So last in first out, whatever data is there, that will be retrieved back first, and that's what has happened here. 65 has gone to 01f location, and then we again pop it now 04 to the next location. So this is how our program has been working, and this is how this stack works. And okay, this we will also discuss, will also deal with this particular problem, like starting stack pointer address is 01 07 by default, and it is colliding with the register 0 of register bank 1. So there are many cases when we'll be using register 0 of register bank 1. In that case, the stack data can conflict with the register bank data. So in that case, what we'll do, as soon as we start the program, if this such cases are arising, we can move the stack from somewhere else. That can be done by simply changing the stack pointer. So now if write like move sp comma hash, we can make it outside this complete 32 bits of the data. We can make it like 56h. Okay, so now our stack will start from 56. Now it will be no longer will be starting with the 0xf. 017 or the register bank 0 data. So let's first compile it, build target, and then start debugging. Let's run it one by one. Now as soon as we move 56, stack pointer data is 56. Now if we press 0, so this register bank 0 data will go to this 57th location. So here 54, 55, 56, 57th location data in RAM, and we move forward. It has gone there. So now our stack is starting from here and will go up to here, and we now keep pop up. Next we go pop is 1F. So this 65 has gone to 1F address, and similarly 04. So this is how we can manipulate the stack and all the data movement from here and there within the entire RAM. So this is the case when sometime problem occurs. Now moving forward, now we'll talk about some of the call instructions, because we discussed jump, call and ASH. So this particular call instruction, if you remember, okay, so what have we done? Yes, so we can make the entire thing to move somewhere else, like we say, okay, move R0 comma hash 65h, and then we are making a call to some, like here. So this is here address, and we define address like this. So this is the label here, and we are writing some of the commands like move R1 comma hash 65 45h, move R0 comma hash 9x, so it has become 4. Now here we are doing like PSW, we move PSW comma hash 10h, and then we are moving R0 comma hash 87h, and then we are move R1 comma hash 76h, and then we are returning it. So now what we have done, we are first moving in the R0 65 and then moving a call will jump here, and here we are changing the PSW, we are selecting the register bank 3, register bank 2, and then we are moving the data in R0 of register bank 2, R1 of register bank, and then we are returning back, and then we are moving from here. So let's save it and compile it, build target, 0 error, and let's have it. Okay, so let's go to our code, and these are several registers, this is data memory. Let's see what happens. Now R0 65 fine, 65 is there. Now a call here, let's, and program address 17. Now look here, now a call program counter is 02, because it is resembling the next instruction. Now as soon as we press it, it jump here. Okay, all the data has been done. Okay, so let's do it again, as we were writing like jump over. So whatever jump over do, it executes all the code once and come back here. So let's say jump in and then go into it, and now it's doing here. Stack pointer is 9, and move PSW. Okay, it's again jumped over because okay. Oh, let's do it. Let's jump in and then PSW and then R0. So right now it is register bank 2, so 87 is here, and then R1 76 is here, and then return back. Oops, we have not changed the content of the PSW. So right now whatever we will do, we will overwriting the content of the register 1 of the register bank 3. So because this particular instruction, this is called the subroutines. So when we call it subroutine, that means this particular instruction has been executed. So if we write it like move R1, so R1 content has been changed, that was of register bank 2, and again this register bank 3. Now as we are not jumping now after this, so this code will run it again and then return. It is starting from 0. So there is some problem in this, it goes haywire because we have not properly defined instructions. So generally most of the times SJMP instruction is written there, and which keeps on jumping to somewhere else. So this is how we can use, or these were the little introduction about assembly language programming and about Keil and how to program on Keil, and that's all. So I hope you learn how to use Keil and how these various instructions work, how to set how to do push and pop operation, how to set various register bank, choose various register bank, and how to make our data transfer among them. So in our next video we'll talk about delay subroutine through assembly language program and a blinking LED program, and then for the simulation we'll do a simulation of that. So that's it for this video.